Hello and welcome to Learn Data. It's great to have you on this channel. I'm Nilesh, and in this video we'll continue our discussion on Gaussian mixture models. Here we are going to uh, get some intuition about the Dirichlet process, uh, finite Gaussian mixture models, and variational inference. So these are involved topics. We won't be going into the derivations, but by the end of this section, I hope you get some intuition about how each of these work when so that when we use the methods in scikit-learn, you know what the changes to a particular hyperparameter would do in the algorithm to find the clusters in the data set. So why we would be using uh, these methods that we are going to talk in this section. And the reason is because it's not always possible that we know how many clusters there could be in the data set. And that's where the Bayesian nonparametrics comes in, and that uses the Dirichlet process. By nonparametrics, uh, what I mean is that there are lot many parameters. It's so there could be infinite parameters. In Bayesian process, again to reiterate, the idea is that what we are trying to find are the parameters that best represent the data in a cluster, the cluster data points. So to find those parameters, we start out with a prior, which is a prior belief of what the values of those parameters could be. This could be the mean standard deviation. Now, to get that prior, we can sample it from another distribution, and then in presence of the data. So after we see the data, which is uh, going to be the likelihood, how does that update our belief in the prior? That is to say, we find the posterior with uh, the information that we get after looking at the data. So that's the whole thinking behind what we are going to discuss now. It's based on this particular part right here. So the posterior is proportional to likelihood into prior. So we have some idea about what the data what the parameters should be to represent the data that uh, we have here, and that's what we are trying to maximize is this particular part, likelihood. And where then this non-parametric Bayesian methods are useful. So here is a very crude example. Let's say we have a cluster, we have data, and we are trying to cluster vehicles by their fuel type. So the vehicles could be running on petrol, gas, um, or they could be running on diesel, electricity, or they could be hybrid vehicles running on petrol and electricity, or they could be running on solar power. And let's imagine a hypothetical situation where every month there is a new technology that is being developed that adds a new type of fuel source to run a particular vehicle. And so each month we are getting a new fuel type that can be used. So as the data comes in, as the year progresses, we'll have new clusters to be found that are not yet known on the present day. See what I'm saying? So what we are trying to find is if there are unknown clusters that may come up in the future, but we can prepare a model that takes into account what those takes into account or creates room for those unknown clusters ahead of time. So when they do appear, the model is able to work with those newly added cluster data as well. Another example is, uh, let's say we are trying to segment people based on their interests. So let's say in the month of January, the interests of a particular group of people, a cluster represented by a cluster in a dataset, is reading, traveling, running, doing nothing, just lying around, or painting. And there may be others as well. Now, as the year progresses, if there are holidays, weekends, or if there are festivals, or if they have some other plans that come up, then their interests could change over time. And so, in order to accommodate those new interests, we need a provision in the model that could handle that. Otherwise, we would have to go back and retune everything from scratch and then to account for each of those new clusters that come into the dataset. So non-parametric Bayes helps us in those situations which can handle infinite number of clusters. So we do not have to specify the number of clusters ahead of time. Although in scikit-learn, we do need to specify the maximum number of clusters, just so that the algorithm would then stop at that point. And here are a couple of definitions. What is a latent variable? Uh, a latent variable is a variable that is unobserved. So earlier we saw that Z was the latent variable, which was representing the clusters. So if we do not know what clusters are there, so that's kind of latent variable. Now let's look at the difference between binomial and multinomial. The reason is why we are looking at this is because the Dirichlet distribution is based on the multinomial distribution. So in binomial, we can imagine a box which has two types of balls. We have green colored and orange colored. So we can draw a green or orange ball from this box with replacement. That would be like a binomial case. Multinomial case, we we can have any number of colors in the box, and we could have any number of balls in the box. So we can draw uh, n balls with n colors from that particular box, and we'll have a probability value associated with that. And Dirichlet distribution is based on that idea, so it's an extension of the multinomial. Another term that we'll be using in this section is conjugate pair. What do I mean by that? Now here we have this Bayesian formula. We have the parameter that we are trying to find based on given the data is equal to this likelihood into prior upon evidence. And if we look at the proportions, if we skip this denominator, then we have this posterior is proportional to likelihood into prior. And the conjugate pair is between, let's say in this case, the normal, the prior is a conjugate pair of likelihood if these are normal distributions. And what that does is the output that we get, which is the posterior, is also the same distribution as the prior. So when we update our prior belief after seeing the data, the distribution that we have, the updated distribution that we have is also of the same type. So that's easier to work with as it's in the same type of distribution. So again, this is beta distribution is a conjugate prior for binomial, and then we have Dirichlet distribution that is a conjugate prior for the multinomial distribution. So the posterior is also Dirichlet distribution. Now the beta distribution and will be, this is a very important distribution. Here this is shown by this particular relation right here. For moment we can ignore this term, which is a normalizing term, that is to bring the values between 0 and 1. We look at these on the right hand side, we have the parameter mu. So this mu is not the mean, it's the parameter, and then these two are the hyperparameters, and the gamma function, this capital gamma is given by this relation shown here down below. And for the values of this distribution, when we integrate it from 0 to 1, uh, it should integrate to the value 1. And this is how the distribution looks like. We have the parameter mu on the x-axis and the probability on the probability values on the y-axis, and we can see that when the value of the parameters alpha and beta, which is a and b here, that those are 1, then we get a horizontal line. So that's showing us a uniform distribution. Then we have set them to a lower value of 0.5, 0.5. Then we get this blue curve, which is like a U-shaped curve, which is kind of pushing the values towards the edges as 0 and 1. And then we have the other shapes that are based on other values. You'll see that I'll be switching the notations based on the sources that I've referred to, but I'll try my best to mention them by showing them with the arrows right here. So this mu is also mentioned as rho in future slides, and this alpha beta, in this case, previous slide we saw that this was A and B. In future slides we would uh, also be referring to them as A1 and A2. And then we have the notation for Dirichlet distribution, which is a generalization of beta distribution. So the beta distribution, like we see here, we have two parameters A and B, two hyperparameters. In Dirichlet distribution, we can have any number of hyperparameters, so which is shown here by alpha k. And again, this is the normalizing term right here, and we have the gamma represented by this notation shown here, and that's the mathematical form for the Dirichlet distribution. And we'll be using this in what is called as the Dirichlet process. And this is a comparison without the normalizing term, and as you can see, two hyperparameters, and here we can have k hyperparameters. Now let's look at how we can let's look at the Dirichlet process, how we can use the beta distribution Dirichlet process to generate data, to assign data points to a particular cluster. So again, we start out with this uh, in our background, which is the posterior is proportional to likelihood multiplied by prior. What that is telling us that we start out with prior values for a parameter, that can be drawn from a distribution such as a normal distribution. And then what we want to see is, after looking at the data, how those parameters get updated, and that would be our posterior. So here, let's say we have two clusters um, shown by the orange X and the green X, and the probabilities of data points, each of these data points associated with this distribution right here and this distribution down here is represented by row 1 and row 2, and so those add up to 1. Total is 1. So how are then the data points assigned to these, each of these clusters? So uh, we create a variable z of n. What that variable does is it um it is uh, let's say it holds the values of probability of each of the data points uh, for the values of probability that comes from the distributions that represents the clusters. So what that helps in doing is it helps assign a particular data point either to cluster A or cluster B, either to cluster this cluster or that cluster, or in other words, we have the values of probability, so we can say to what extent a particular data point would belong to a cluster which is represented by orange or which is represented by the green X, right, shown here. And those values for the row which is comes so here we have the mu representing shown here in this equation, so that is the same as row, so both of these mu would be row 1, and we can then use the beta distribution to get those values. Next, we can look at how we can generate data given the parameters part of likelihood. So here we can get the values for xn from a normal distribution with a mean mu for that particular zn cluster for a specific cluster, and the covariance for that particular cluster. Now, in this particular case, what we do not know is the mean of each of these clusters. So to start with, so those are the parameters. So to start with, what we can do is sample them as a prior from a normal distribution. So as shown here, we can use n normal distribution with mean of mu0 and sigma and covariance as sigma 0 to sample the prior mean and covariance for each of the clusters that would be represented by mu k. So here we would have the two mu1 and mu2. Secondly, what we do not know are the probability values row 1 and row 2, and we can get those values from the beta distribution. So to the beta distribution, we would input A1 and A2 parameters to get the values for the probability row 1, and then row 2 we can calculate it by subtracting row 1 from 1, and the the total of these would be 1, and the reason why we just have row 1 and row 1 row 2 and not row 3 is because we just have two clusters. Now here are some interesting plots. So the relation that is shown here up top, the hyperparameters are shown as a and b, and that's what I've written here. A is equal to 1, b is equal to 1. However, in the previous slide, I've shown them as a1 and a2. I hope that's not too confusing. So the very first plot on top here, what we have are the values for row 1 and row 2, which add up to 1. At least they should. We have this value that's slightly above 6.6, and this value is slightly below zero point 0.4, so that should be close to 1. And what these are telling us is this is just one sample for uh, from the beta distribution that is telling what the probabilities would be for a data point to lie either in cluster 1 or cluster 2. If we sample row 1 several times, maybe 100 or 1000 times, and we try to plot the distribution looks like what we see here in the bottom histogram. And it's close to a uniform distribution. Not exactly, but close to a uniform distribution. Now, if we change the values of the hyperparameters a, b to 0.01, 0.01, that is to say we are reduced, we are inputting very small values. In that case, the probability shifts to the um, the cluster row 1 in this case. And if we try to plot the histogram, if you sample this several times and if you try to plot the histograms, the reason why that is because the probability is shifting to the edges, and that's what we saw by the U curve in the distribution plot that we saw for beta distribution in earlier slides. That's shown here. So we have peaks at 0 and 1, and then uh, there are bars right here, but they are the height of those bars is very, very small. Then after this, if we on the flip side, if we increase the value of the hyperparameters for the which are the input to the beta distribution, we see that the values of probability for row 1 and row 2 are pretty similar. So it's like equal weightage is given to both the clusters. And we sample row 1, let's say several thousand times or several hundred times, and if you plot them, we get a distribution which looks like a normal distribution as shown down here. So it's telling us that uh, there is equal mass on each of these. So these could be the points that are on the decision boundary of the between the two clusters. And finally, we have uh, a situation where the value for the hyperparameter a is higher, much higher than 10 times higher than the value for the parameter b. And we can see that the final histogram is skewed and it's not symmetric. Now, so far we looked at what we would do if there were two clusters. What happens if the number of clusters is more than 2? That's where the Dirichlet distribution comes in. And Dirichlet is a generalization of beta distribution, as we saw earlier. So we have more than 2 hyperparameters because we have more than 2 classes now. And it is given here. So the probability that we would get from a Dirichlet would be from 1 to k. So those minimum number of probabilities we can get as many classes there are in the dataset. So here we have input of hyperparameters. So the number of hyperparameters again would be 1 through AK or 2 AK based on how many clusters are there to be found. And so that's what we discussed. Now row K again should the values for row should again sum up to 1. So if we have 3 clusters, the value of row 1, row 2, row 3 should sum up to 1. And now for the values for the means, we can sample them again from a prior conjugate. Here it is shown by a normal distribution with mean mu0 and covariance sigma 0, and those means are represented here by the x's for each of the clusters. Now again as before, we have Zn which can be used which can choose assignments for data points to clusters, and that is done based on the values for probability row for each of the clusters. And finally, to get the data, we can use the the mean for the cluster to which the data point would be assigned, Zn, and the covariance sigma. And those are tied into the relation that we have up above, which is the likelihood and the prior. So again, here on the left hand side, we would have these data points allocated or associated with the distributions that are represented by the mean and variance associated with these x's. Now, to visualize the Dirichlet distribution, we have on the left hand side in this particular plot, we have 4 classes. So, sorry, 4 clusters. And when we set the value of hyperparameter A or alpha to 1, all of them 1, then we get a distribution, discrete distribution such as shown here. And if we pull just row 1 and sample it several times, we get a distribution shown down below, which is not uniform as compared to what we saw earlier for the beta distribution, which was very close to the uniform shape. Again, as similar to the beta distribution in case of a Dirichlet distribution, if we reduce the value of the hyperparameters to let's say 0.01, then we see the similar behavior as we saw with the beta distribution, where the probability mass gets shifted to the edges. And so here we have row 1 and row 4 that have probabilities much higher than 0. The rest 2 are closer to 0, and if we sample row 1 several times and plot it, we see that 2 bars at 0 and 1. And again, similar to the beta distribution, now when we sample from a Dirichlet distribution with the values for hyperparameters which are much higher, so if we set it to 1000, then the probability values for the row 1, row 2, row 3, row 4 are similar. So in this case, they would be 0.25. And if we pull row 1, sample it several times, we get this nice Gaussian looking curve distribution for the probability distribution. That was it for this video. I hope to meet you all in the next video, where we'll continue our discussion on Gaussian mixture models in part 4. Please like, share, and subscribe. Thank you.